Welcome back to Talk Tensors, everyone. You know we love to take deep dives into the latest and greatest machine learning papers, and today we have a really cool one.
Yeah, this one's super interesting.
We're talking all about cross-modality image matching.
Basically, being able to match up images from totally different sources.
Like, think about a doctor combining a CT scan and an MRI to get a super detailed view of your brain.
Or a self-driving car that can use both its regular cameras and thermal sensors to navigate in the dark.
Exactly. That's the kind of future this paper is pointing us towards.
It's really exciting to think about all the insights we could uncover if we could connect information from different kinds of images like that.
It's like finally having all the pieces of the puzzle and being able to put them together.
Right.
So the paper that's got us all buzzing today is called Match Anything: Universal Cross-Modality Image Matching with Large-Scale Pre-Training.
Catchy title.
It is catchy, right? And it's by researchers at Zeji Young University.
A lot of great work coming out of there lately.
Absolutely. In a nutshell, they've created a model that can find pixel-perfect connections between images from completely different sources.
Things like CT scans and MRIs, or even photos taken with a regular camera and thermal images.
And that's actually a problem that's been really tough to solve in computer vision for a long time.
Traditional image matching algorithms are great when you're comparing apples to apples, you know?
Like two photos from the same camera.
Exactly. But when you start trying to match up images from different sources or modalities, things get a lot harder.
It's like trying to compare apples and oranges.
Both fruit, but totally different.
So how did these researchers crack the code? Well, they basically tackled it from two angles: data and training.
Makes sense. Gotta have both.
First, they gathered a massive and super diverse data set.
They threw everything in there but the kitchen sink, right?
Pretty much multi-view images with 3D reconstructions, video sequences, single images. They even warped some images to create variations.
That's clever, using the same image in different ways to get more variety.
Right. This approach was crucial because it exposed the model to a huge range of appearances and structural differences, making it much more adaptable to new types of images it hadn't seen before.
They were really trying to make it robust.
And then there's the training aspect where things get really clever.
I love when the training gets clever.
Me too. They use this technique called cross-modal stimulus.
Cross-modal stimulus.
Yeah, basically they used image generation techniques to create synthetic cross-modal image pairs.
So, like, they might take a daytime image and turn it into a nighttime image while preserving the structure of the scene.
Right, it's kind of like showing a language student different translations of the same text.
Ah, I see. So they get a deeper understanding of the underlying meaning.
Exactly. So this match anything model is essentially learning to see past the superficial differences in how an image looks and understand the core structural elements that are consistent across different modalities.
That's pretty amazing when you think about it.
It is right. But before we get too deep into how match anything works, let's take a quick step back and look at the historical context of image matching.
Always good to know where we came from.
Right. So early attempts at image matching relied on something called handcrafted features.
Basically, rules designed by humans to identify key points in an image.
Exactly.
And those worked okay for single modality matching, but they struggled with cross-modality tasks because the differences were just too great.
Right. The appearance of the images was just too different.
It was too much for those handcrafted features to handle.
Then came along the deep learning revolution, and everything changed.
Oh yeah, deep learning was a game changer for so many fields.
Absolutely. We started using convolutional neural networks, or CNNs.
Which can learn features directly from the data.
Exactly. And this led to huge improvements in accuracy. But cross-modality matching still remained a challenge.
It was still tough to get those different types of images to play nicely together.
Right. One of the main roadblocks was the lack of large-scale labeled cross-modal data sets.
It's hard to train a model if you don't have enough data.
Exactly. And even when researchers did have data sets, the variety of modalities and scenes was often pretty limited.
It's like trying to learn a language from just a few phrases.
Not very effective, right?
Not at all. So to overcome this hurdle, researchers started getting creative with how they created training data.
Like generating synthetic data, using things like image style transfer.
Ah, so instead of just relying on real images, they started creating their own.
Exactly. And these methods definitely helped improve things.
But they still fell short of achieving truly universal cross-modality matching.
It was still work in progress.
And that's what makes this Match Anything paper so significant.
We were really pushing the boundaries.
Right. They combined a massive and diverse training data set with that clever cross-modal stimulus strategy.
And the result? A pre-trained model with exceptional generalizability.
It's like they created a Rosetta Stone for images.
Now, that's a great analogy.
Right.
Okay, so let's unpack how they actually built this match anything model.
Yeah. Let's get into the nitty-gritty.
As we mentioned, the training data was a mix of three main sources.
Multi-view images, video sequences, and single image datasets.
Right. Let's start with multi-view images.
So these are images taken from different viewpoints of the same scene.
Exactly. And especially those with 3D reconstructions.
Ah, so you can actually see the scene from every angle.
Right. And that's valuable because it provides realistic viewpoint changes and ground truth correspondences.
Ground truth correspondences, meaning you know exactly which points in each image correspond to the same point in the 3D model.
Exactly. Think about it like a 3D model of a building.
Okay, I'm picturing it.
You can render images of that building from any angle, and you know exactly which points in each image match up.
That makes sense.
So they use datasets like Megadepth and Blended MVS, which have tons of images from different viewpoints, along with their 3D reconstructions.
Great data sets.
Yeah, they're fantastic. This allowed them to create training pairs with accurate ground truth correspondences by basically warping images from one viewpoint to another.
So they're basically simulating different viewpoints using the 3D model.
Exactly. But the thing is, multi-view datasets tend to be relatively small and limited in their diversity.
So they needed something more to really scale up their training.
And that's where video sequences come in.
Ah, video sequences are great because they capture real-world perspective changes.
Right. But they don't typically come with ground truth correspondences.
So how do they work around that?
They got clever. They developed a course-defined strategy to create pseudo-ground truth matches.
Pseudo meaning kind of fake, but still useful.
Right. And they did this by tracking points across video frames.
Tracking points.
Yeah, imagine following a specific detail like a doorknob as the camera moves through a room.
Okay, I can picture that.
By tracking that doorknob across multiple frames, you can kind of infer its position even if you don't have a precise 3D model of the room.
That's pretty ingenious.
It is, right?
Yeah.
And with this approach, they were able to leverage the massive amounts of video data available online to create even more training pairs.
So they're really taking advantage of all the data that's out there.
Absolutely. Now, the third type of data they used was large-scale single-image datasets.
But a single image doesn't give you any correspondences on its own right.
You're absolutely right.
So how did they make that work?
Again, they got creative with image warping techniques.
Image warping.
Yeah, they basically applied random transformations to the images.
Like stretching or rotating them.
Exactly. And that created synthetic image pairs with perspective changes.
So it's like taking a picture of a painting and then holding it at different angles to create slightly different views.
Perfect analogy. So now they had this huge and varied data set of image pairs.
That's a great start, but what about the cross-modal stimulus strategy we talked about earlier?
Yes, that's where the real magic happens.
I knew there was more to it.
So remember, this involved using image generation techniques to create synthetic cross-modal image pairs.
Right, they weren't expecting the model to perfectly match a real thermal image to a visible light image just from these synthetic examples.
Exactly. The goal was to push the model beyond just memorizing how to match specific modalities.
They wanted it to learn those fundamental underlying structural cues that are consistent across any type of image.
Regardless of the source.
It's like teaching a child to recognize the shape of a cat, regardless of whether it's a cartoon, a photo, or a drawing.
Exactly. So they used techniques like image style transfer to transform one image from each training pair to a different modality.
So like taking a picture of your house during the day and making it look like it was taken at night, but the house itself stays the same.
Precisely. The idea wasn't to create perfect replicas of real images.
It was to force the model to focus on the structure of the scene.
And that brings us to the end of part 1 of our deep dive into Match Anything.
We've covered the training data and the training strategy, but the big question is, how well did this model actually perform?
We'll be diving into those results in part 2, so stay tuned.
Can't wait. Welcome back, everyone. So before we got sidetracked talking about training data...
Oh yeah, we were really getting into the weeds there.
We were. The big question is, how well did this Match Anything model actually work?
Yeah, let's get to the good stuff. And spoiler alert, it's pretty impressive.
Oh yeah, they really knocked it out of the park with this one.
Okay, so they started by testing the model on medical imaging.
A classic use case for image matching.
Right. They used a data set of aligned brain images that included CT scans, MRIs, PT scans, and SPECT scans.
Wow, so they were really covering all the bases.
They were. And get this, the ROMA model, which is a detector-free matcher.
Detector-free meaning it doesn't rely on predefined features.
Exactly. It showed a 76.9% improvement on average across all these different modalities when trained with their Match Anything framework.
That's huge. 76.9% is a massive jump in performance.
Right. And think about what that means for doctors,
They could potentially spot subtle abnormalities much earlier.
leading to faster intervention and better outcomes for patients.
Exactly. Early detection is key for so many diseases.
And it wasn't just brain images either.
Oh, really? They tested it on other parts of the body, too.
They did. They also tested it on a liver CT MR dataset.
Interesting. So combining CT and MRI data for the liver.
Right. And the ELOF-TR model, which is another type of matcher.
ELOF-TR, that's a deep learning-based
Yeah.
method, right?
And it's known for its accuracy and robustness.
So it's a tough one to beat.
You got it. Well, guess what? With their framework, it achieved a mind-blowing 423.7% improvement.
423.7%. Are you serious?
I'm dead serious. That's not a typo.
That's insane. It's like they found a cheat code for image matching.
Pretty much. It just goes to show how powerful their approach really is.
Okay, so Match Anything is crushing it in the medical imaging world.
Crushing it is an understatement. But what about other applications?
Like what? Give me some examples.
Like giving robots night vision.
Okay, that's cool.
Right. They tested the model on thermal and visible light image registration.
Which is essential for things like self-driving cars and search and rescue robots.
Exactly. They evaluated it on a bunch of different data sets, including satellite views, aerial views, and ground views.
So a wide range of scenarios.
And it consistently outperformed existing methods, even those specifically designed for visible thermal matching.
So we're talking about robots that can see in complete darkness, firefighters who can see through smoke to locate victims, and cars that can drive themselves even in bad weather.
You got it. It's pretty mind-blowing stuff.
It really highlights the potential for Match Anything to improve safety and efficiency in so many areas.
Couldn't agree more. And they didn't stop there.
Oh, there's more.
Oh, yeah. They also tested it on matching visible light images with SAR images.
SAR images, what are those?
SAR stands for synthetic aperture radar.
Okay, I've heard of that, but I don't really know what it is.
It's a type of imaging technology that uses microwave radiation to create images.
Microwave radiation.
Yep. And this allows it to see through clouds, fog, and even darkness.
So it's like a superpower for satellites.
Exactly.
Mhm.
It's incredibly useful for things like environmental monitoring, disaster response, and intelligence gathering.
Wow, so matching a SAR image to a visible light image must be super difficult, right?
You'd think so, but Match Anything handled it like a champ.
No way, seriously.
Seriously. They used a data set of SAR and visible light image pairs taken from satellite views.
Okay, interesting.
And both the Roma and ELOF-TR models, trained with their framework, showed significant improvements over previous methods.
So this model can handle everything from medical scans to robot vision to satellite imagery.
It's like the Swiss Army knife of image matching.
That's a great way to put it.
But I'm sure there are some things it can't do right.
Well, no model is perfect, right?
True.
One area where Match Anything struggles is matching aerial view images to ground view images.
So like trying to align a satellite image of a city with a street-level photograph.
Exactly. That's a tough problem even for humans.
I can see why the perspective shift is so dramatic.
It's like trying to match a photo of a Lego model to a photo of the real building it's based on.
Perfect analogy.
Yeah.
And why do you think the model struggles with this?
Well, the training data for Match Anything didn't include many examples of these extreme perspective changes.
So it just hasn't seen enough of that type of data to learn the patterns.
Right. It's not that the model is incapable of doing it, it just needs more training data.
So there's room for improvement.
Definitely. And that's actually a very exciting opportunity for future research.
Oh, yeah. I see where you're going with this.
Could we adapt Match Anything to handle these extreme perspective changes?
Maybe by incorporating data from drones or satellites that capture both aerial and ground view simultaneously.
Exactly. If we could crack that, it would open up a whole new world of applications.
Imagine being able to seamlessly connect satellite imagery with street-level data for things like urban planning disaster response, or even creating hyper-realistic virtual reality experiences.
The possibilities are endless.
So Match Anything is clearly a game changer for image matching.
It has the potential to revolutionize so many fields.
But like any powerful technology, there are ethical considerations to keep in mind.
Oh, absolutely. We can't just ignore the potential downsides.
We'll explore those and some other novel notions after a quick word from our sponsors.
Stay tuned.
And we're back. All right, so we've spent this episode talking about Match anything. This groundbreaking development in cross-modality image matching.
We've seen how it works, the impressive results. It's gotten even some of its limitations.
Now let's shift gears a bit and talk about some of the exciting possibilities this research opens up.
Yeah, this paper has really got people thinking about the future.
One area that I'm particularly fascinated by is this idea of bridging the gap between the physical world and the digital world.
Using match anything.
Exactly. How do you see that happening?
Well, think about augmented reality or AR.
Where digital objects are layered onto our view of the real world.
Right. Right now, AR relies heavily on visual cues to align those digital objects with the physical environment.
But what if we could use match anything to incorporate data from other modalities?
Like depth sensors or thermal cameras.
So instead of just relying on what we see, AR could use a much richer understanding of the physical world.
Things like depth, temperature, even material properties.
Exactly.
Yeah.
AR experiences could become far more immersive, interactive, and responsive to the environment.
Think about an AR game where virtual characters react to the temperature of objects in your room
Or an AR shopping app that lets you try on clothes that drape realistically over your body no matter how you move.
That's taking virtual reality to a whole new level.
And it's not just about entertainment either.
Oh, definitely not.
This technology could revolutionize fields like education, healthcare, and manufacturing.
Imagine medical students using AR to visualize anatomical structures during surgery.
Or engineers using AR to overlay design schematics onto real-world objects during assembly.
The possibilities are pretty mind-blowing.
And speaking of mind-blowing stuff, let's talk about how Match Anything could enhance artificial intelligence, or AI.
AI is already changing the world as we know it.
But how could this research take it even further?
Well, one area that's ripe for innovation is multimodal learning.
Where AI models are trained on data from multiple sources.
Right now, most AI models are trained on a single modality, like images or text.
But with Match Anything, we could fuse data from different modalities, like images, text, and audio.
Creating AI systems that have a much richer understanding of the world.
So it's like giving AI the ability to experience the world more like humans do.
To sight, sound, and language.
Exactly. Imagine an AI assistant that can understand not only what you're saying, but also interpret your facial expressions, your tone of voice, even the context of your surroundings.
We could start to see real human-like intelligence emerging.
Okay, now I want to take our speculation even further.
Further, how much further can we go?
What if we could use Match Anything to connect real-world data to data from simulations?
That's an interesting thought.
Simulations are great for research, development, and training.
But they often lack the realism and complexity of the real world.
But if we could use Match Anything to bridge that gap, we could create simulations that are much more accurate, realistic, and effective.
Think about training self-driving cars in virtual environments that perfectly replicate real-world roads.
Complete with weather variations, traffic patterns, and even pedestrian behavior.
Or training surgeons in virtual operating rooms that accurately simulate human anatomy.
They could practice procedures and refine their skills without any risk to patients.
That would be a game changer for medical training.
And it's not just limited to those fields.
Right, we could use it to train pilots, astronauts, architects, anyone whose job involves interacting with complex systems.
We could create simulations that are indistinguishable from the real thing.
Allowing for safer, more efficient, and more effective training across so many professions.
It's clear that this research has opened up a world of possibilities for combining information from different sources.
It's pushing the boundaries of what's possible in augmented reality, artificial intelligence simulations, and countless other fields.
The Match Anything paper has given us a glimpse into a future where we can seamlessly blend the real and the digital,
creating experiences and applications that were once pure science fiction.
And while there are still challenges to overcome, and ethical considerations to address the future of this technology is incredibly exciting.
It's safe to say we're just scratching the surface of what's possible.
It's going to be fascinating to see what new innovations and breakthroughs emerge as researchers continue to explore the potential of Match Anything.
I can't wait to see where this all goes.
Well, that's all the time we have for today, Talk Tensors listeners.
Thanks for joining us on this deep dive.
We hope you've enjoyed it as much as we have.
Match Anything is a true testament to human ingenuity and the power of technology to shape our world.
Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible.